In the previous lecture, we were discussing exact equations, exact ODEs, maybe. Today, we are going to discuss known exact ODEs, equations which are not exact equation, but we can make them exact. What happened to this thing? Let me adjust the camera. Okay. Known exact, which can be made exact, non-exact ODEs, okay? But we can convert them into exact ordinary differential equation of the first order. What was the criteria for exact equations? To be exact, it was if the differential equation is of this form, m of xy dx plus n of xy dy is equal to 0. The criteria to be exact was is partial m or partial x. No, partial m or partial y. The coefficient of dx should be differentiated with respect to y. It's a partial derivative. And this should be equal to partial n over partial x. If this is true for this differential equation of first order, then we say that this differential equation is exact. If this is exact, then there must exist a function which is the exact differential of this left-hand side of this equation. Okay, then that is, and there exists a function f of x y such that df must be equal to m dx plus n dy. This was the criteria. Then we say that f of x y is equal to c must be the solution of this differential equation. This was the procedure of finding exact equation. Now, what if the equation is non-exact? Non-exact. In this case, obviously, if partial m over partial y is not equal to partial n over partial x, okay? If this is so, then how can we make that original differential equation? We can convert them into an exact differential equation. First of all, in short, in short, or in an other notation, we can write this thing my is equal to, it should be equal to nx. Okay, the subscript with m, it denotes partial derivative of m with respect to y. Okay, and nx means partial derivative of n with respect to x. This is the partial derivatives notation. Okay. So I hope you know it. Now, if the differential equation, if the first order differential equation, this one, if for example, this one, this is equation one, if it is not exact, that is, it doesn't satisfy this criteria, then what do we check? Then we have different cases, but we are going to discuss here two cases. There are more, but here in this book, only two cases have been discussed. The case one is if my minus nx divided by m or n let me check it. I always n. Yes, this is n. N. If this expression, if this fraction, because we know my, what is, or m, we know it, we can compute partial m over partial y, we can compute partial n over partial x, and we have n and m here in the equation. So my minus nx divided by n. If this expression or the fraction gives us a function of x only, we obtain some function mu of x, which is a function of x only. Okay, where mu of x is a function of x only. Remember this thing. Then this function will be the integrating factor for this equation 1. And what do we do with the integrating factors? We multiply integrating factor on both sides of the equation. Okay. So if this is the integrating factor, then we should multiply this factor on both sides of the equation. Okay. Multiplying mu of x on both sides of equation 1. What do we obtain? We obtain a new equation, mu of x times m of xy dx plus mu of x n of xy dy equal to 0. So we obtain a new equation. Okay. Now this is our new m of xy. We can call it m bar of xy dx plus n bar of xy dy equal to 0. We call it equation 2. Now this equation must be exact differential equation. Okay, this equation will be exact differential equation. Now this is the case 1. Similarly, we have another case. Let me define all the cases and then we'll discuss these things with the help of examples. The case 2 is if, now we change that thing, nx minus my divided by m. If this expression, let me check, I have written the correct expression. Yes, okay. I did a mistake here. Then in the case 1, the integrating factor in the case 1, then the integrating factor is let me check here. And the integrating factor is it is exponential of mu of x dx. This is the integrating factor. Okay, if we call it, it's again a function of x, and you can call it maybe some other mu bar of x, maybe. Okay. This is mu bar. Okay, remember, if this expression is a function of x only, then integral exponential of integral mu of x dx is the integrating factor. We call it mu bar of x. So here we must have mu bar, okay, or some other notation you can use here. Now, in the case two, if this is this expression is a function of x, sorry, function of y only, you can take some maybe lambda of y, okay, where lambda of y is function of y only. Then integrating factor, maybe lambda bar of y is what? It is exponential of lambda of y dy. This is your, this will be the integrating factor. Then after getting the integrating factor, you multiply the original equation with the integrating factor. And this integrating factor will convert the original differential equation into an exact differential equation. So in that case, this is your case one, and this is your, in that case, lambda bar of y m of x y dx plus lambda bar of y n of x y the dy is equal to 0, and you can call it m bar and you can call it n bar. And we get the similar equation, this one, but in this case the integrating factor is different. So this will convert the given differential equation into an exact differential equation, and you can check whether the converted differential equation, this one, is exact or not by verifying that criteria, partial m over partial y is equal to partial m over partial x. Okay, let's do these things with the help of examples. If you have any question, you can ask me. Okay. Let's try to solve this equation. Example, solve the following ODE. It's xy dx plus 2x squared plus 3y squared minus 20 dy equal to 0. So this is your original equation, and we have to solve it. Now, we can solve it by some other technique if it is possible. But if it is not possible, then we try the exact technique. Now here m of xy is what? It is xy, x into y, sorry, x into y, and n of xy is equal to 2x squared plus 3y squared minus 20. Now check whether this equation is partial m partial y, and this is our m y. With respect to y, it is x, and nx is what? It is 4x. I hope you can calculate it. Now these things are not equal. My is not equal to nx, so the equation is not exact. So equation 1 is not exact. We cannot solve it by using technique of exact ODE. Now let's try whether this equation can be converted into exact equation or not. So for that, we check two cases. Case 1, my minus nx divided by what was it? M N, this thing. We compute this thing. Now, what is this? My is x, nx is 4x divided by n is 2x squared plus 3y squared minus 20. And this cannot be solved. Yes? No. It is neither a function of x nor a function of y. Not a function of x only, not a function of. So this is not equal to a function of x only. Function of x only means this is not equal to mu of x. So case one has been not successful. So we go for the case two. Case two is nx minus my divided by m. Okay, now we draw this expression. Nx is what? 4x. My is what? X divided by. What is m? It is xy. Now this is what? 3x divided by this, and we get 3 by y, which is some function of y only. That is true. We obtain a function of y only. So the case two is possible. It's true. Now, what would be the integrating factor in this case? The integrating factor will be, let me go to the other board. So the integrating factor is h of y e raised power 3 by y dy. And integrating, we can take 3 outside, and what is the integral of 1 over y? It is log of y. And we can take this 3 on the power here, e log cancel, y cube. We obtain y cube. This is the integrating factor. We now multiply this integrating factor on the both sides of a given equation, and we obtain this thing. Now, this is your new m. Okay, this is your m bar of xy, xy 4, and what is your n bar? It is this whole thing. It is 2x squared y cube plus 3y 5 minus 20y cube. Now, you can check whether this new equation is exact or not by computing my. My is what? It is 4xy3. And nx, it is what? It is 4xy cube. Again, you can see that these two things are equal. If this is equal, then we can say that the given differential equation is exact. So equation 2 is exact. Okay. Equation 2 is exact. Is exact equation. Now we can solve it by using the technique of exact first order differential equation. And how do we solve it? We start with partial. We say that partial f of partial x is what? M of xy, and partial f over partial y is n of xy. Okay. In fact, if this is exact, we assume that there exists a function f of xy such that partial m over partial x is equal to m of xy and partial f over partial y is equal to n of xy. Okay. We assume that there exists a function f of xy such that the left hand side of this equation is the exact differential of this function f of xy. Furthermore, partial f over partial x is equal to m and partial f over partial y is equal to n. This is the complete description of this thing. As we had discussed, that if the equation is exact, then there must exist a function f of xy whose exact differential, whose differential is the left hand side of this equation. Then we try to find that function. Okay, now we are going to find this function f of xy, which is unknown. We assume that. How to find it? By using these two equations, which we discussed in the previous lecture. If you don't know about these equations, you can go back to the previous lecture and listen that. Till now, if you have any question, you can ask me. Now, I told you in the previous lecture that we can start with any of these two equations. If we call it 1 and if we call it 2, we start with the 2, maybe. But the 2 is, n is difficult here. You can see m is easy to handle. So we should start with the first equation. Okay. It's your choice. You start with any of these two equations, but look at these functions, m and n. Okay. It is easy to integrate this one as compared to this one. So I should start with the first equation, which involves m. Okay. So starting with 1, I can write partial f of partial x is equal to m. It is x y power 4. Now what we do, we take the integral on both sides with respect to x, integrating both sides with respect to x. It gives me f of x y on the left hand side and the integral of x y 4 with respect to x here. Okay, remember this. Plus a function of y, which is the integrating factor here, because we are assuming that y is a constant. So if y is a constant, we can take this y power 4 outside of this integral, and we are left with only integral of the function which involves x only. Now this can be integrated. It is x squared by 2, 1 by 2, x squared by 4 plus g of y. So this is your f of x y. Okay, this is your f of x y, but only thing which is unknown here is g of y. So we need to compute g of y first. Now, in order to compute g of y, in order to compute g of y, we use the other equation. Partial f over partial y is equal to n. So partial f over partial y is equal to n. Now, as we have f, we can take its partial derivative with respect to y. And then we have n as well. We use this thing. Partial derivative of this thing with respect to y is nothing but 4 divided by 2 x squared y cube, 4 y cube, because x will be considered as constant. And this should be equal to, plus g dash of y is equal to n. What was our n? It is written over there. It is 2x squared y cube plus 3y5 minus 20y cube. Okay. Now you can see here that this term will be cancelled with this term, and we are left only with g dash of y, which is 3y5 minus 20y cube. This is g dash, but we require g of y. So integrating with respect to y, integrating with respect to y. What do we get? We get g of y is equal to 3 by 6 over 6. So it is 1 by 2 y 6 minus 20 is by 4 over 4. And 4 5s are 20. It's by 4 plus a constant of integration. If you write this constant, it's okay. If you don't write, then it is again okay. I told you why. Now, if we have this g of y, we insert this g of y here in order to complete our f of xy, okay, which will be our solution. And we put that solution f of xy is equal to c in order to get the one parameter family of solution. I told you in the previous lecture. Why is it so? I hope you get it. If you have any question, you can ask me. Integral जो लिया था? Have you seen the previous lecture? In the previous lecture, I told you while computing integrating factor, we can add a constant here. यहाँ पे. But whenever you multiply this integrating factor on both sides of the original equation, that constant can be taken common and that can go to 0. Integral. This one? यहाँ पे. I cannot listen you. Can you talk?
Yeah, okay. So over here, with this step.
Yes. Okay. The constant has been added. G of y is a constant. It's a constant of integration because you are dealing with partial differentiation and partial integration. Okay. यहाँ पे what did we have here? यहाँ पे your expression partial f of partial x is equal to x by 4. This is a partial derivative. Okay. In partial derivatives, for example, if it is a partial derivative of f with respect to x, we assumed that y is a constant. Okay. If you have assumed that y is a constant, so whenever you integrate this function with respect to x, you do not add a simple constant. As you have assumed that y is a constant, then while integrating that function partial f over partial x with respect to x, you will add a function of y as a constant of integration. Okay, why is it so? I explained this thing in the previous lecture. Let me explain you once again. Partial f over partial x is m. M is your what was m? X by 4. Yes. This was yes. Now, in fact, this f is a function of xy originally. Okay, f of xy. In order to get partial f of partial x, this thing, what should be f of xy? It should be 1 by 2 x squared y 4. Okay. Now, if you take partial derivative of this thing, partial f of partial x, what do you obtain? You bring 2 down. and then 2 pi out minus 1. So it becomes what? X by 4. X by 4. Okay. Now, if you have here maybe 2 by 5, when you take partial derivative of this function with respect to x, this term will be 0 because there is no x here. This is treated as a constant. And even if you have some other constant here, this will be 0 as well. Okay. So 0 plus 0, if this is your function, its partial derivative with respect to x will be the same. Now, whatever you have here, a function of y, that might also constant, that might also contain a constant term as well. Okay. So this whole term will become 0. In order to compensate this term, what we do when we integrate this thing with respect to x, you take the integral only with respect to x. You are assuming that y is constant here. So whenever you take integral of this thing with respect to x, you are assuming that y is a constant. If you're assuming that y is a constant, then the constant of integration should be a function of y, which I have added here as g of y. Now this is a more generic term for here as a constant of integration, because this term might contain function of y as well as a constant. So that's why we are taking g of y here. I hope you get it. If you have any further questions, you can ask me. I give you a couple of minutes to see these things. Then you can ask me any question if you have. So that is how we can convert a non-exact differential equation into an exact differential equation. But it is not mandatory or necessary that every non-exact differential equation can be converted into exact differential equation. It is not necessary. It might not be converted into exact differential equation. It is possible that the both cases are not true. Okay. We do not obtain a function of x only or a function of y only in case 2. If that is true, then we cannot convert the given differential equation into exact differential equation. We try some other technique. Okay. I'll give you another example that you people try it. Try to solve this differential equation. It is not exact. You have to convert it into exact differential equation. 2y cube, 2y square, 2y square plus 3x b x plus 2xy dy equal to 0. Try this equation. Check whether it is exact differential equation or not. If it is not exact, then try to convert it into exact differential equation and then solve it. Okay. I give you a few minutes to solve it. Try it yourself. If you face any difficulty, you can ask me any question. The case 1 is true. Here, when you compute the expression my minus nx divided by m, n, then that will be a function of x only. Then you can compute the integrating factor, and multiplying the given equation with the integrating factor, you can convert this equation into exact differential equation. I hope you must have solved it. At the end of the lecture notes, there are exercises which you can do for practice, and other exercises are given in the book as of Dennis Giesel. You can try some exercises from Dennis Giesel book as well. If you have any problem, if you have any question, you can ask me. So next thing which we are going to discuss after exact differential equation is the direction fields. Direction fields. Direction field is a graphical method for displaying general shape of the solution, general shape or general behavior of the behavior of the solution to the first order ODEs. Graphical, okay, is a graphical method for displaying general form of the solutions, family of solutions of the differential equation without solving them, in fact, okay. So what is direction field? Is a method of displaying graphical shape. Its shape means we cannot compute exact shape, but if we, of course, if we use some kind of computer to compute direction field, that would be exact form, but manually it will not be exact form of that solution because there might be some error. It's a method of displaying graphical shape of the solution of first order ODEs. Okay. First order ODEs, that is what? dy by dx is equal to f of xy. Okay. In fact, without solving them, without solving first order ODEs. Okay. Now, what is this dy by dx? Dy by dx is the slope gradient of a function y with respect to x of some function. Now we know that this gradient is equal to f of xy. Now f of xy is what? Is the value of the gradient. Okay. So if we have two variables x and y, we assume that they are independent variables in this function. Okay. Now, sorry. Now, if D is the domain, if we assume that D is the domain of these two variables, x and y, where you can say that x varies between a and b in this interval, and y varies between c and d in this interval. Okay, it means x belongs to ab and y belongs to this interval cd. Now, what this domain is geometrically, it is a square domain. Okay, it is a square domain where x varies between a and b. Okay, and y varies between c and d. So this is your domain. It's square domain. Okay, we're assuming here y is a dependent variable. Y depends on x, but here we are assuming that y is independent variable, okay, which varies between c and d, and x varies between a and b. Because if you are considering this as a function f of xy, then it should be z is equal to f of xy. We assume that x and y are independent variable. Z is the variable which depends on x and y both, because this will be a surface function, a two-dimensional function. It's not a single valued function, okay? Single variable function. It's a two variable function now. So its graph will be a surface, not a curve. So if you want to compute a surface, then your domain should be a two-dimensional domain. Okay? This is not a sphere, it is some kind of rectangular domain. Okay, it depends what are the values of a, b, and c, d. And these two intervals are basically subsets of real numbers. And this is a subset of what? This is a subset of R cross R, or R square. Okay? Because this is your x-axis and this is your y-axis. In fact, it will be a three-dimensional function. Okay, z direction goes to the third dimension, x, y, and z. Now, on this domain, we are going to try to plot this f of x, y, okay, at different points. Now, let me define the grid or the partition. If this is domain, D is what? This is A, B cross C, D. Then the grid of the domain, we call it grid, we call it partition. Let's take this thing with the help of example. Let's start with the help with these things with this example. For example, if this is your ODE, dy by dx is equal to what is 0.2, 0.2 x, y. This is your ODE. And the domain is maybe, what is given the domain here? Boom. -5 to 5, -5 to 5, cross -5 to 5. This is the domain of this differential equation. Okay. Now, if this is your f of x, y, okay. Number one, what do we compute here? What we can compute? If we compute f of x, y at some point here within this domain, this is a domain from, sorry, -5 to 5. Okay. Here, for example, here you have 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So this is your -5, this is your 5, this is your -5, this is your 5. Okay, this is your 0. Your 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay. If you choose some point here, maybe 2, 3, this one, and you compute f of x, y here at 2, 3, it will be 0.2, 2, and 3, and to the 6, 6, and 2 to 1.2. Okay. Now, what is this? It is your f of x, y, and it is the derivative dy by dx. It's a slope. Okay. At this point, you draw a line segment, a small line, which has a slope 1.2. Now you can imagine what would be a slope 1.2. It would be something like this. Okay, its slope is, or its gradient is 1.2. Okay, so approximately this thing. This thing is called Lionel element. Okay, so this is Lionel element. Okay, a Lionel element is what? It is small piece of line which passes through the point and which shows the slope at that point corresponding to this equation right inside fxy. We can compute Lionel elements as many as we want, but within this domain, -5 to 5 and -5 to 5. For example, you can compute a Lionel element for some other f of maybe -1 and x -1 by 2, 0.1, -1, and 2. It is what? Negative 0.4, negative 0.4. So now at this point, -1 to 2, this is your point, and the slope of slope is at this point is negative 0.4. So it should be like this one, maybe. Okay. So slope here is negative 0.4. In order to show whether the slope is negative or positive, you can add a small arrow here as well. Now, this shows that this slope is increasing. So slope is positive. Here you can put an arrow here on downward. This shows that the slope is negative. Okay. So these are what? These are called Lionel elements. Okay. We can compute as many Lionel elements as we want, but within the domain. Okay. Now, the next thing is what we do. We have partitioned this domain. We have partitioned this domain into small pieces, okay, which is called a grid. Okay, this is what? This is called a grid. Means you have partitioned the domain into small pieces. Okay. What kind of grid is this? It is in fact, it's a kind of a rectangular kind of. You can see it in my notes. It will be, in fact, it's a kind of. Let me show it. Should I show it in? Let me share you the screen. That would help me. What is grid? We divide this thing. I hope you get what is a Lionel element. You remove these lines. Let me. The grid is in fact you divide the x domain, the domain of x -5 to 5, into points. For example, here you divide it into points -5, -4, -3, -2, -1, 0, 1, 2, 3, 4, 5. Okay, as we have divided here. Similarly, this is the domain of x. You also divide the domain of y, -5 to 5. It could be different. You can divide it into some integral pieces. 1, 2, 3, 4, 5. Now, corresponding to each value of x and y, you can make a point. Okay, So your points would be -5 to 5, -5, -5, -5, 5, 5, -5, and 5, 5. You take all the combinations with 5 and 5. Okay, this and that. This with 5. You can take some other as well. So you take all the possibilities of these points, and these points are basically this one, this one, this one, this one, this one, this one, and these are your grid points. Okay, these are your grid points. Okay. These are the all possible points if you take the combination of these numbers within the domain X and Y. So you obtain these points. Okay. So these will be 5 power 5. 5 power 5, 125 होंगे कितने होंगे यहाँ पे it's a 5 times 5 125 sorry 25 25 25 25 and then 5 5 5 5 ये कितने हो जाएंगे टोटल हाँ so 25 25 25 100 and then 5 5 5 5 20 21 so it's 11 square 11 square hoga 121 points so these are you divide all this domain into points okay. So here also you have points okay all these points make a grid okay, of the given domain. Now at each grid point, you can compute a Lionel element. Okay? You can compute infinite many Lionel elements, but you have to stay up to some limit. Okay, you cannot compute Lionel element at each point because these are real numbers. Okay? They are uncountable. So you divide the domain into some points whose values are integers. Okay, that's the easiest possibility of dividing a domain into points. To divide the point into the domain into points, you obtain the grid, the domain grid of the domain. Okay. Now at each point of the grid, you can compute a Lionel element. Okay, you can compute a Lionel element. Those Lionel elements will show you the pattern of the curves, pattern of the family of solutions of the given differential equation. Okay. For example, you compute these Lionel elements on all these grid points, and this is in fact you can compute them. You can see in my notes, it's written over there. It's the pattern of the curves are in fact here. It's this thing, and here it's maybe this thing. Here it is like this. Here it is maybe this thing, and you can compute Lionel elements on all the points. And then you can see that you can draw a curve. In fact, what is this? These Lionel elements are what? It's a tangent line. It's a tangent line at the point, at some point on the function, on the curve. ठीक है? किसी भी कर्व, किसी भी फंक्शन के जो ग्राफ है कर्व पे, उस पे आप किसी एक पॉइंट पे टेंजेंट लाइन कंप्यूट करें तो वो क्या है बेसिकली it's a straight line passing through that point. In fact, what is these Lionel elements? These are basically equation of tangent lines. So not equation, it's these are tangent lines on the graph of the function at that point. Okay. And what is the criteria here in order to compute the curves? The curves should pass through these tangent lines at exactly one point. Okay. Now, if you want to compute a function, maybe here it is. If you want to compute a function which represents the solution, the curve should pass through, it should come here, it should pass through this point at one, it should touch it exactly once. Here, it should touch it exactly once. Here, it should touch it exactly once in the middle. It should touch it exactly once in the middle. It should touch exactly one in the middle. Okay, yes.
So, for example, over here, you get a family of parameters.
Right?
You get like a family of parameters. You won't just get one parameter.
Yes, we have to get one parabola as a solution. I don't get your, can you?
But we have so many linear elements.
Yes, we have so many linear elements. We will have so many curves, which will be the solutions. Okay. Here you would have this kind of curves. Okay. Which pass through the linear elements exactly at one point. Okay. So these will be the shape of the solutions. Now, what solution is what one solution, single solution? You're looking for single solution. Whenever you don't have an initial condition, you get a family of solutions. In order to get some particular solution, you must have some initial condition, which I told you. Now, if there is some initial condition along with this differential equation, for example, I say that compute the solution of this differential equation with initial condition y at maybe 0 is equal to 0. Okay. Y at maybe 2 is equal to some maybe 2 or 3, whatever. Now we'll see that which curve is passing through this point. In fact, this is a point. This is value of x and this is value of y. Now we'll see which curve is passing through this point. Okay. Now this curve, when we have value of x2, 0, 1, 2, and value of y3, 0, 1, 2, 3. So this one, so this curve is passing through this point. That is why our particular solution is only this curve, not the other ones. I hope you get it.
Sure.
Ji beta.
Sir, I was just confused that like how did we get the other curves? Because like for example, if we have one point xy, we're getting a curve for that function only, right?
There'll be infinite many linear elements. You agree with this?
Yes.
Okay. Now we can connect the dots of linear elements to get the curve, but the curve should pass through these linear elements exactly once, and it should go along the flow of linear elements. We cannot draw a curve which doesn't go along the flow of linear elements. I hope you get it.
Yes, that makes sense. I'm just confused that like how do we get the other curves?
So that is why we can draw all the curves which go along the flow of the linear elements. Those curves will be infinite many. Okay,
yes. Makes sense.
You'll get infinite many curves. Okay, if your linear elements, sorry, if this is your linear element, there will be again another linear element here. You cannot start a curve which passes through this linear element and this will equally pass through this linear element. This is not possible. The curve should go along the flow of the linear elements. You cannot do this thing. One curve is passing through this, and then you go there and pass through this linear element. This is not possible. Okay? You cannot change the flow of the curve, flow of the linear elements. There'll be infinite many linear elements. You have to draw the curve along the linear elements. So here you would have infinite many curves, which all will give you the family of solutions, one parameter family of solutions, because the parameter is a real number as well. If you change the value of that parameter, the curve will be changed. And if you have this initial condition along with the differential equation, then you have to look at these curves. Which curve is passing through this point? That curve will be your particular solution. Okay. Let me show you this thing, maybe somewhere here. उसमें तो वो account नहीं खुल रहा. Let me show you here. Just a second. Here, I hope it will be visible. No. No. This thing. Sorry. This thing. Now, this is in fact the solution of this differential equation graphically. On the picture, on the top, you can see that the linear elements have been displayed on all the grid points. Okay, you can see the linear elements are basically rotating in the middle kind of thing. Okay, now in the picture below, you can draw curves which pass through these linear elements, but you have to go along the flow of the linear element. If you start with some particular linear element, the curve should follow the flow of the linear elements. So how many curves would be there? How many curves we can plot here? We can plot infinite many curves. Okay, so this is basically generally the form of the solution, the shape of the solutions. Okay. Now, what particular solution do you need to have for your differential equation? For that, you should be given an initial condition, and you see that which curve is passing through that point. That will be your corresponding solution. Okay. I hope you get it. You can see the pictures clearly. Yes.
Yes, sir.
That will be your singular solution, maybe, which doesn't follow the pattern of curves. Singular solution cannot be obtained from the general solution. Okay, there are other solutions. These are not only the solution curves. This is only the general shape of the solution of the family, one parameter family of the solutions. These are the general solutions. We can obtain particular solution from these curves. Okay, but remember that I told you there is some kind of singular solutions of the given differential equation as well. We cannot obtain those singular solutions from the general solution by giving some specific value to the constant c. So singular solutions are not displayed here. They are still hidden within these curves. Maybe we don't know. So we cannot find singular solutions by using this technique, by direction fields. Yes.
Should we try to interpolate it? Find the function, or
no, if someone asks you to find the solution of this differential equation which passes through this, then you have to mention which curve is the solution. Okay, you just leave it as. Then further, you can draw another picture. You can draw a single curve on that graph as well in order to show your solution. You can see here in my notes as well, I have I have shown these things. Maybe I have computed these curves. Okay, this is basically the grid. You can see the grid here. Okay, these are the solutions. Here is another thing which we need to next time we'll discuss it. Isoclines. Isoclines is the solution curve whose slope is constant. Okay, we'll discuss isoclines in the next lecture. Or it's very simple thing. You can read it. All the solution curves or the solution of the differential equation who are straight lines. ठीक है, ठीक है. जो straight lines होंगी solutions में, those straight lines are basically they are made up of those Lionel elements whose slope is same at all those points. Okay. If the slope at certain points are same, then they will form up a constant, sorry, a linear line, a straight line. That straight line will, we call it isoclines. There are isoclines in the solutions, one parameter family of solutions of the differential equation. Those isoclines are what we'll discuss it in the next lecture, and why, how do they help us in order to further analyze the solutions. If you have any question, you can ask me. Otherwise, we are going to stop it here today. This is a very interesting topic. You'll see that this has many applications when we'll go to discuss the application of differential equations. Using direction fields, we cannot find singular solutions. We can only find general and particular solutions, one parameter family of solutions. Okay. Singular solutions are difficult to find because you can only see them hidden within the solutions or within the equations. Okay, we are discussing only the techniques which gives us one parameter family of solutions. Okay, or the particular solutions. Singular solutions are very difficult to find for any differential equation because they do not follow or technique or method of solving those differential equations. They can be computed with by observation or some other technique, because singular solutions are not the special cases of the general solutions. Okay? You can find them, but by using some unusual techniques. Usual techniques से तो general solution ही आएंगे, ठीक है, ये particular solutions हैं. वो भी still they are difficult to find for many kind of differential equations. जो general solutions हैं या particular solutions, they are still difficult to find. Not all differential equations are solvable. A very few kind of first order and very specific second order differential equation are possible to solve. Not all. अगर ये वाली जो है ना, ये x एक्सिस वाला है, ये जो कर्व होगी ये भी सॉल्यूशन होगा, but this is if y is equal to 0, this equation is what? Y is equal to 0. So you can see that y is equal to 0 is a solution. Okay, you can draw it as a solution as well. Okay, so I told you there are infinite many solutions. This one. There might be other possibilities as well, which we have missed here while drawing this. Okay. So, but this is the general pattern of the Lionel elements or the solution curves. But there might be other solutions as well. Okay. As I told you, particular solutions and singular solutions, but in fact, they do not follow this pattern. Singular solutions, they do not follow this pattern. But y is equal to 0 is following this pattern. Okay, you can see that whenever you expand this domain, this curve will also expand. So that's it for today. If you have any further question, you can ask me. Otherwise, I'm going to stop this video. Okay, then see you in the next lecture.